As you can see from the title of this video, this tutorial is about classes and properties of matter. As we push on into a bigger description about chemistry more so than branches in the scientific method, we are going to find that this idea that is matter is a very important driving force behind everything that we'll talk about throughout the entire year. To talk about the classes of matter and the states of matter, which are the main two things we'll look at, you're going to find out this is going to take a majority of the school year because each one of the individual classes and states of matter has a great amount of information that goes with it. If we're going to talk about properties and classes of matter, we're going to have to get some definitional things out of the way because I'm going to start to throw some terms around and I want you to have some background on what they are so that when I use them, you can understand what it is that I mean. In terms of characteristics of matter, I wanted to define the following things. First, what matter is. By definition, matter is anything that has mass and takes up space. Everything that you can think of in the physical world is defined as matter because they all have mass and they all take up space. Things that relate to matter will be things like measuring it, right? How big, how much, this and that. The first way that we measure matter is by getting its mass. Mass is a measure of the quantity of matter. Right? It is finite. It does not depend on anything else. The more matter there is, the higher the numeric value for mass. We will use balances in the back of the lab to measure mass. This next term I only introduced to avoid confusion between an everyday understanding of how we measure what things are in terms of their size, right, and how we will do it in the chemistry classroom. Weight and mass are two very different things. Mass exclusively measures the quantity of matter. Weight measures the quantity of matter, however, it also has to incorporate the force of gravity. The greater the amount of gravity there is on an amount of matter, the higher the numeric value. We use scales to measure our weight, which is gravity dependent. The big difference in how I can highlight this to you is we know that we measure our body in pounds, in kilograms, depending on where you live. That is what we call weight. It is dependent upon what the gravity is. Where I live, my weight is about 175 pounds. That is very, very dependent on the gravity. If I were to go to the moon, the gravity on the moon is only 1/6, roughly what Earth is. So my weight on the moon would be 1/6 what my weight is on Earth. That is why when you see the astronauts on the moon and moon landings and things, they can bounce and very, very slowly fall to the ground because there isn't nearly as much gravity on the moon. Mass, on the other hand, is not dependent upon gravity whatsoever. My mass, right, on Earth is a certain number. On the moon, that number is exactly the same because it strictly measures the amount of matter my body possesses. It does not count on gravity. So we are going to really think about not focusing at weight at all, and I will always talk about things in terms of mass. Some other definitional stuff that I want to discuss with components of matter are the following terms. I will use the word atom a great deal. Right? Atoms are the smallest unit of an element that maintains the properties of that element. Right? When I ask what is the smallest piece of matter that we will focus on, we are going to generally treat that as what we call the atom. There are subatomic particles. Protons, neutrons, electrons, quarks, things like that, muons. But we are going to think of the smallest piece of matter for this class as the atom. Right? And I will use the atom to build larger things that we still call matter. The other thing that gets associated with matter is that all matter possesses energy. Energy is the ability to cause change or do work. All matter has energy. There are a lot of different types of energy. I have chosen to focus on two as we start into our discussion of matter. That is kinetic energy and potential energy. There are other things. Thermal energy, solar energy, things that you will probably hear. These are not the only types of energy. These are simply the two that we're going to relate to the most in class. Kinetic energy is the energy of motion. It's the energy of movement. Right? Things have to be in motion for it to be described as kinetic energy. Right? There are many people that study kinesiology. Right? All that is the study of the movement of something, people. Potential energy is what we call stored energy. The potential energy is positional dependent. Right? Depending on where your position is, you may have more or less potential energy. A very simple way to highlight this would be to bring out your everyday tennis ball. Right now, as I set this tennis ball onto the countertop there, the tennis ball has no kinetic energy. It is not moving, and I'll hold it up here just in case that's out of the screen. It has no kinetic energy if my hand is perfectly still. It does have potential energy because I have lifted it up off of the table. Right? It has stored energy that could be changed into kinetic energy. This leads us to one of our laws. And remember, there are very, very few laws out there. We have many theories, but laws are accepted things that are uncontrovertible, true facts. And one of them is called the law of conservation of energy. It says, energy can be converted from one form to another, but it cannot be created or destroyed by ordinary chemical means. Ordinary chemical means not nuclear. Whenever we start to get into nuclear reactions, everything kind of goes out the window when it comes to things of this nature. Here's what an example of that would be. I cannot increase or decrease the amount of energy that something has. I can simply change it. If I were having this ball right here perfectly still, it has no kinetic energy. It has a certain amount of potential energy. The higher up in the air this ball goes, its potential energy increases. But that energy must come from somewhere. So when I move the ball up to here, you may say, well, here it had 30 joules of energy. Here it has 100. Where did the extra 70 joules of energy come from? Well, if you notice, I had to move the tennis ball from one location to another. Movement is kinetic energy. So by me lifting the ball from this height to this height, I transferred kinetic energy into the tennis ball, which now allowed it to have a larger potential energy. The same thing can happen in reverse. Right now, this has zero kinetic energy. It's not in motion, but it has a decent amount of stored energy, potential energy. The way I can get that to convert is simply by letting the tennis ball go. As it fell down, the potential energy was decreasing. Simultaneously, the kinetic energy was increasing. So we were getting no net gain or loss of energy. It simply changed its form. And energy is an idea that we will keep hitting on throughout the course of the year. I didn't take the time to rewrite these because the definitions are almost identical except for a few words. There are also two other laws. The law of conservation of mass and the law of conservation of matter. These two things say identical claims to the law of conservation of energy, except anywhere that you see the word energy, you replace it with mass or matter. For instance, the law of conservation of mass says mass can be converted from one form to another, but it cannot be created or destroyed by ordinary chemical means. Same thing holds true for matter. Matter, law of conservation of matter, says matter can be converted from one form to another, but it cannot be created or destroyed by ordinary chemical means. A simple way of thinking about this would be if I looked at, say, a sheet of paper. This sheet of paper possesses a certain amount of matter that leads to a certain mass. If I had this piece of paper undergo a chemical reaction, I were to light it on fire and burn it in a combustion reaction. The claim of law of conservation of mass and matter says that if I were to gather up all of the ashes that this paper burnt into and tracked any of the gases that were given off when it burned and added those masses up, they would weigh, their mass would be identical to whatever the mass of this complete intact sheet of paper was. So you have to understand that matter and mass can't be created or destroyed. They can simply change their form. So these are some definitional things that we wanted to discuss before I jumped into your classes of matter so that you knew what I was talking about when I went through. If we look into the classes of matter, there are really only two major classes of matter, but we'll subdivide it just a little bit more. And if we look at classes of matter, we'll start simply matter. Right? Matter is the largest classification of what we can think of. It's anything that has mass and takes up space. The first thing we'll tend to ask ourselves is, can it be separated? Because if it can be separated, that will classify it into one of two categories for us. If it can be separated, it is what we're calling a mixture. If it cannot be separated, it's what we refer to as a pure substance. I cannot take it apart based on its properties. That's going to get us into three very major topics that we'll discuss throughout the course of this year. Mixtures, elements, and compounds. And that is what I tend to classify as your classes of matter. Mixtures, elements, and compounds. Yes, elements and compounds are pure substances, but they are also their own individual categories. So when I ask what are the classes of matter, I want you to think mixtures, elements, or compounds. Well, what are each of these things? Well, a mixture, by definition, is a blend of two or more kinds of matter where each retains its properties. So a mixture could be an element put with a compound. It could be an element mixed with another element. It could be a compound mixed with a compound. But the take-home message is that every single part of the mixture retains its individual properties. There's two different types of mixtures. You have homogeneous mixtures and you have heterogeneous mixtures. Homogeneous mixtures are mixtures that look like they're only one thing even though they are not. They say they have uniform composition or that the composition is uniform. Sometimes it's easier to learn these things by examples of things. Some good examples of a homogeneous mixture would be something like Kool-Aid. Everyone could tell me that Kool-Aid isn't one thing, right? The Kool-Aid, the stuff we drink, right, has a couple things in it. It has water, which is a compound. It has sugar, which is a compound. And it has food dye, which is a compound. So there's three different things that are in Kool-Aid. However, when I mix those three things together, it looks like one thing. I hold up a glass of Kool-Aid, you can't see the sugar separated from the food dye, separated from the water. It all looks like one thing. That is a homogeneous mixture. Air is another great example of a homogeneous mixture. Right now, I could pretend to scoop up a giant handful of air that you're looking at, and it all looks the same, even though air has a lot of different things in it. It has oxygen, nitrogen, carbon dioxide, small amounts of helium. There are lots of different things, which were all elements, by the way, that go into that mixture. The main idea is they keep their properties. That's why when I breathe in air, I breathe in oxygen and I get the benefit of oxygen's properties and my body can process it. While at the same time, the air that a plant breathes in, their main component that they take is carbon dioxide. They take in carbon dioxide so that they can undergo photosynthesis to produce their energy. So the idea is that they're homogeneous mixtures, but the things that make up the mixture keep their properties. A heterogeneous mixture is still a mix of all of these elements and compounds. The difference is you can see the difference when you look at it with the naked eye. A great example of a heterogeneous mixture would be a salad that had anything but just lettuce in it. Right? If I make a salad with lettuce, tomato, onion. If you're from where I'm around, you put things like French fries and steak and chicken and all of those into it. We can still see all of the pieces, and the chicken still tastes like chicken. The lettuce still tastes like lettuce. The tomato still tastes like tomato. Each has its own properties, but we can see them. That makes it a heterogeneous mixture. Other good examples would be granite. And if you look at a granite countertop in your house, you can see the little specks in it. Because you can see the specks, that means it's heterogeneous. Same thing with wood. If I break a piece of wood open, you can see the different pieces of wood involved. That makes it a heterogeneous mixture. But the big thing is they retain their properties. The other category of matter they call pure substances, and I've been hinting at elements and compounds as both being examples of these. And we will spend a large majority here in the first half of the year learning about elements and compounds. Starting simple, elements simply cannot be separated into simpler substances. They are as defined as they can be. I can't break gold into smaller subdivisions of gold. It is the simplest thing. So if I take a giant handful of a gold necklace or a silver chain, that is all silver. It can't be boiled into two other new things. Elements are the things you find on the periodic table. Three that I chose, gold, silver, oxygen, are all examples of elements that you cannot separate into something small. You can change what it looks like, but you can't make it simple. Compounds are a combination of elements. They're made of two or more elements in a fixed proportion. They come together the same way every time. For instance, water, H2O, is a compound. It comes together the same way. Fixed proportions, meaning unchanged. Proportion, meaning a number ratio. So what happens is water is always H2O. Salt comes together the same way. It's sodium chloride. It comes together as NaCl. Na is the element sodium. Cl is the element chlorine. It's two elements, right? But they come together in a fixed proportion, a 1-to-1 ratio. Carbon dioxide is CO2. Carbon is an element. Oxygen is an element. They come together in a fixed proportion, always 1-to-2. If I get a ratio that is different, that means it's an entirely different compound. Right? It is something that is not carbon dioxide. For instance, CO, C1O1, is carbon monoxide, and it has totally different properties than carbon dioxide. And we'll learn more about that later on. But these are your classes of matter: mixtures, elements, compounds. To add a little bit to what elements are, I put some properties of elements up here that we're going to talk a lot about here in the next couple weeks. There are three categories of elements. You have metals, nonmetals, and metalloids. To help me out with what I'm going to talk about with this, I have a periodic table here that I'm going to tape up to the board so that we can highlight something that the periodic table does for us. First thing that we want to learn about is that a lot of the elements on the periodic table are what we call metals. Metals possess certain properties. Those properties are listed underneath. Metals are good conductors of heat and electricity. Metals are malleable. Metals have luster. Metals have good tensile strength. They stay together as wire. And they're very ductile. How can I tell if an element is a metal or not? Well, if I have a sample of an element, I can test for each of these things, and if it fits those categories, then I'd say yes, it's a metal. If I know what it is, the periodic table will tell me if it's a metal or not. I'm claiming that metals lie to the left of the staircase. Well, what am I talking about when I say that? Well, if you look at any periodic table, you will notice that starting with the element boron and going down and over every row, is a black line or a red line that seemingly divides the table into two pieces. Not in half, but into two separate pieces. All of these elements over here, and all of these elements to the right. Any element, which you'll notice is a very, very large amount, because these all belong in the left side, are what we call metals. Anything to the left of the staircase is a metal. So if I said, is vanadium, right here, a metal, non-metal, or metalloid, you'd tell me it's a metal because it's to the left of the staircase. If I asked you to predict its properties, you'd tell me it's a good conductor of heat and electricity. Right? If I left it out in the sun and I put my hand on it, I would get burned. You would tell me it's malleable, that it can be hammered or shaped. Right? Iron is a great example. To the left of the staircase, tons of things are built by shaping and hammering iron. You would say they have luster. Luster means that they are shiny. These get into your fancy metals that tend to cost more. Gold, silver, platinum. They're very shiny, all because they're metals. Good tensile strength. That means it stays together as a wire. Copper is a great example of something that has good tensile strength. It stays together as a wire, and it's ductile. It's easily made into wire, so that many of the things that run your computers, that run your phone lines, that run all of the electricity in your house tend to be made of copper because we can make it into a wire easily and it stays that way. All because it's a metal, it's to the left of the staircase. Non-metals, on the other hand, are to the right of the staircase. So I look things that are on the right side. Notice there are significantly less of those non-metals. Non-metals, as opposed to memorizing a list of things, I simply remember the exact opposite of what metals are. So if I went through this list and I remembered, oh, metals are good conductors of heat and electricity, non-metals the opposite. It's a poor conductor of heat and electricity. Metals are malleable, non-metals are brittle. They break when we hit them with a hammer. We can't shape them. Metals have luster, non-metals don't have luster. Metals have good tensile strength and are ductile. Non-metals have poor tensile strength and ductility. And the opposite of the word luster tends to be dull. If a metal is lustrous, it's shiny. Non-metals, the opposite, they are dull. The last category that elements can fall into are metalloids or metalloids. Metalloids, if I'm looking for them on the periodic table, touch the staircase on the top or bottom. So if any part of the box that the element is in is touching the staircase, we would define it as a metalloid. That's not 100% true, but for the purposes of this course, we are going to treat that as being true, that everything that touches the staircase is a metalloid. I'm claiming that metalloids have characteristics of both metals and non-metals. And that sometimes leads to confusion. People are going to say, well, how can something be both shiny and dull? How can it be a good conductor of heat and a poor conductor of heat? They're not. What they do is they mix and match properties from each of these. For instance, a metalloid could be a good conductor of heat, but be brittle as well. It could be malleable, it could be hammered or shaped, but it has poor tensile strength, where if it was a metal, it would have good tensile strength. So it's not two things opposite at the same time. It's one of these properties with a different one of these properties the other way. One of the most useful metalloids that we have is silicon. Right? So much of what computers run on are these silicon chips. And the reason that silicon is very useful as a metalloid is because it is a very good conductor of electricity, so it can run our computer, but it is a poor conductor of heat. It won't overheat the computer. So the silicon is a good conductor, which says it's a metal, but it's a poor conductor of heat, which makes it a non-metal. That is why it's a metalloid. And if you notice, silicon, Si, lies right above the staircase. It touches the staircase as element 14. So these are a lot of the things that have to do with classes of matter and types of elements. The last thing with matter I wanted to talk about are states of matter. And states of matter are not elements, compounds, and mixtures. States of matters are what we talk about with solids, liquids, and gases. These here are visual. What do they look like? Is it a solid, liquid, or a gas? There is a fourth state of matter called a plasma. We don't tend to focus on it that much, so I'll touch on it right here very quickly. But A plasma, a high temperature state similar to a gas where atoms lose electrons, only exist at very extreme temperatures. Or we can create that sort of scenario, right, like in an incandescent light bulb. Right? But we tend to think of them as just very, very, very hot gases. We'll get into much greater detail with solids, liquids, and gases. Like for instance, whenever you think about these states of matter, I always want you to think about what their particles look like. For instance, when I think solid, this is the picture I want to pop into your head. That we have a lot of particles. They could be elements. They could be compounds. Right? They could be a mixture. But the thing you need to remember is that their molecules are very close together. This would be a great example of what a solid looks like. And I have this in class all the time. Right? But for your notes, I wanted you to have that picture. Right? This right here shows how solids are packed incredibly tightly together. They have a definite shape and volume. Right? It is a shape that won't change. This solid, for instance, would look like a cube. The volume of a cube can be found. Right? A volume, a length times width times height of a cube. It is fixed. It doesn't change. The reason it doesn't change is because solids have very strong intermolecular forces. And we could talk a whole nother period on intermolecular forces. All I want you to know about intermolecular forces is that it's the stuff that holds things together. Right? Intermolecular forces are attraction forces that make things stay together. Liquids are very similar to solids with one slight difference. Liquid molecules are close, but they possess the ability to slide by one another. Solids are not in movement. They are not in motion. They're in fixed positions. They're stuck. Liquids have the ability to slide, like sheets of paper, one on top of the other. This makes liquids have a definite volume, but an indefinite shape. They take the shape of whatever container they're in when they do this. The reason is because they have slightly weaker IFs. Solids' IFs are so strong that this white molecule cannot break away from the other ones it's touching. It's stuck there. The force holding them together in a liquid isn't nearly as strong. It can slide by it and move, which is why if I were to tip this over and it's a liquid, we can pour it. It doesn't get held next to the other molecule. The last phase is a gas, and gases look nothing like this. Right? Gases spread out and fill whatever container. They are not touching. They're constantly in random motion. They're not fixed and shaking. They're not sliding. They are moving very quickly. The molecules are far apart, and it's because they have very, very weak IFs, which is intermolecular forces, that can't hold them together. They can't get two molecules to stay together, right, because the forces are so weak. Over here, I showed you how energy relates to this. And just realize that energy is the stuff that breaks things apart. So if you think of something as packed closely together, if it's packed together, it's not broken up, it's not far apart, it must have low energy. So solids have the least amount of energy. Gases have the most amount of energy. And what it says here to remind you this is more energy equals more motion. The more something has the ability to move, the higher amount of energy that it has. So I hope this helped you out with classifications and some definitional things about what matter is and how we're going to categorize it. And we'll use this as we push on forward into the next 3, 4, 5, 6 chapters. But as always, if you have any confusion about anything or you are wanting to find out more, please do not hesitate to comment.